Tibet, the most dramatic physical feature on the face of the Earth. An arid plateau as large as Western Europe that includes over 3/4 of the Earth's land surface, more than 4 kilometers high. Its southern ramparts, the Himalayas, soar to altitudes well over 8 kilometers above sea level. South of the Himalayas, there's a marked climate change. Verdant slopes are irrigated each summer by the monsoon. The Earth has seen nothing like it before, certainly not for 1 billion years, perhaps over its entire history. No wonder it's thought to have a major influence on the world's weather patterns.
The Earth's climate has been warm for hundreds of millions of years, a greenhouse Earth. Then that Earth began to change. It began to get cooler, first slowly. By about 40 million years ago, there was ice in Antarctica and in Greenland. It got colder still, and then almost in a twinkling of an eye, huge ice sheets began to form, eventually reaching depths of well over a mile. Why did that happen?
The consequences of a vast, high-standing plateau on changing global climate was first realized by Bill Ruddiman.
I was thinking that we might make a major contribution to solving the problem at the beginning of glaciation, partly because uplifted terrain gets cooler and partly because it turns the winds in such a way that, for instance, there's a more northerly flow into North America, into the area where the glaciers grew. So it was a reasonable assumption that it might help promote glaciation.
When Bill came along with the idea that perhaps mountain uplift was changing the wind patterns in the planet in a way that would promote glaciation in high latitudes, bring cold Arctic air further south, this was an exciting idea to me.
John Kutzbach is a climate scientist who experiments with computer simulations of the world's atmosphere. Bill Ruddiman's uplift idea suggested a new experiment. What effect did the rising of Tibet have on the Earth's climate? Kutzbach calculated the effect of Tibet at 3 heights. First, Tibet at sea level.
We've got this box outline where the Himalayan mountains and the Tibetan Plateau are, so you can have that for reference. Then the coloring on here shows the rainfall patterns in the summertime, and you see that there's just a little bit of rainfall here in Southeast Asia and over in Africa. Now if we advance this to our experiment with half mountains, you see that things are beginning to happen. And then if we go to the full mountain simulation, there's even a more dramatic change. Very heavy precipitation on the south and southeast corner of the Tibetan Plateau, over southeastern Asia, and very large dry area extending from the Middle East into the Mediterranean and North Africa.
But what are the physical causes of these changes?
If we had a low-lying continent of this form, you might get a very weak convection cell with rising air spreading out in the upper atmosphere and then air coming in from the surrounding ocean, perhaps producing a little bit of rain along the edges of the continent. But it just wouldn't be a very exciting circulation because there's nothing on this continent to really focus the heating of the sunlight. If instead we place a high plateau on a continent such as this, all of a sudden the sunlight during the summertime has a real focal point for heating this high plateau. So you have very more active currents of air rising over this plateau, spreading out, sinking, and air literally rushing in towards the continent. In addition to the air coming in towards the continent, the spin of the Earth makes the air more or less spiral in. Air coming in off the Indian Ocean, spiraling in over the continent, banging into the Tibetan Plateau, being forced to ascend, producing violent thunderstorms along the face of the plateau.
What Kutzbach had found was nothing less than the Indian monsoon system. This was the direct consequence of the uplift of the Tibetan Plateau.
We had gotten the results out of the computer here in Madison, and I hopped on a plane with a lot of computer output, went to his lab in Lamont, and we spread all of these things out and looked at them.
I remember still with a sense of delight sitting in my office, and we took the results from the model, the general circulation model, and I came to just a very different realization, and I think in a way he may have as well, as to how beautifully the uplift of Tibet changes the distribution of moisture. Doesn't explain everything on the face of the earth, but it has a major effect on the patterns of wet and dry climate and vegetation through the mid-latitudes, not just on the plateau, but well around the plateau, upstream and downstream. The results of the model ended up explaining a little bit of almost everything except what we were after. There was really a very small cooling of the Arctic area and the areas where ice sheets must grow.
Although successful in many respects, the Ruddiman-Kutzbach model was not able to predict large-scale global cooling. They'd not found a likely cause for the ice ages. At this point, enter an enterprising postgraduate, Maureen Ramo, who was just starting her academic career. She looks back at that time 10 years ago.
Just putting the plateau in the models didn't really cause any major global cooling. Like, you couldn't explain why Antarctic ice sheet grew. So it seemed like there still was some other cause for global cooling. This was something I was always thinking about, and obviously thinking about the mountains too, and started going off in my own direction. And it started really with one of the first classes I took where I learned about Berner's model.
Bob Berner's model used the idea that the amount of carbon dioxide in the air controlled how warm the Earth's atmosphere was. This is the greenhouse effect. The more CO2 in the atmosphere, the warmer the Earth's climate. According to Berner's model, the Earth works as a giant pump, shifting the CO2 from the rocks to the atmosphere, to the oceans, and back to the rocks again. Carbon dioxide is pushed into the atmosphere from volcanoes and can combine with rainwater, making a weak acid, which can dissolve silicate rocks on the Earth's surface through weathering. This removes CO2 from the atmosphere. The dissolved material washes into the oceans and is deposited on the sea floor. Eventually, the sediment is dragged down a subduction zone, and the CO2 is returned to the mantle. Global temperatures are determined through CO2 in the atmosphere, controlled largely by the rate of seafloor spreading.
Carbon cycle models ideally will give us CO2 in the past, but the real benefit of studying these models is to evaluate the different processes that affect carbon dioxide, how we circulate carbon from one part of the surface of the Earth to another and to the depths of the Earth. And we can learn more about geological processes by studying the carbon cycle. The goal, of course, of trying to get at what controls carbon dioxide over geologic time.
It was just an amazing model. I read the paper many, many times. I thought it was just so neat, and to think about climate this way.
I've been working on the whole problem of carbon in sediments for a very long time, maybe 30 years. But actually doing modeling of the carbon cycle, we started with my colleagues, Lasaga and Garrels, thinking about the problem around 1980.
Through their model, Berner and colleagues examined the fluxes of carbon that moved around the cycle. Most important for us, he saw the role of mountains as a feedback mechanism. Periods of rapid seafloor spreading led to a hot CO2-rich atmosphere. This increases the rate of chemical weathering that takes place in mountains, thus drawing down CO2 from the atmosphere and returning the Earth to cooler conditions. However, something about the model was wrong. Maureen Ramo.
It predicted that global cooling occurred between 150 million years in general, whereas most of the global cooling occurred actually much later. So there seemed to be this mismatch between what the model predicted and what really happened in geologic history.
Time now to look at that geological history and a journey that takes us onto the Tibetan plateau itself. We join an international group of scientists on a reconnaissance expedition across the plateau. Their findings will help to determine the shape of future research in Tibet. Most of the journey was across inhospitable terrain, over 4,500 meters in elevation. What happened to make the Tibetan landmass so high?
150 million years ago, I would have been standing on the southern edge of the Asian continent. And far away to the south, there would have been an ocean, the Tethys Ocean, stretching for thousands of kilometers. And on the other side of that ocean, there was the Indian continent. Now, plate tectonics dragged the Indian continent closer and closer towards the Asian continent.
The separation of Africa, America, Antarctica, and India happened during the age of the dinosaurs. Continents were driven across the Earth's surface. India drifted north, shrinking the ocean on its northern coastline as it moved. Then, between 50 and 60 million years ago, India collided with Asia.
Here we can see strata which originally would have been laid down horizontally. And now they've been deformed, they've been upturned, they've been folded, they've been totally scrunched about, showing the impact of that major collision.
The Earth's crust thickened as a consequence of this momentous event, pushing up the Tibetan plateau. During the collision, India has moved a further 2,000 kilometers north into Central Asia. The uplift of the Himalayas was the grand finale of this tectonic drama. But while all this mountain building has been going on, there must have been massive erosion at the same time. And these two processes together, uplift and erosion, might explain the pattern of climate change following collision.
You have to cause climate change somehow. If the growth of a Tibetan plateau or in a high area can cause climate change, and then climate change can accelerate erosion, well, then you have what we would call positive feedback. One accelerates the other, and they feed back on one another.
You can do two things to a rock. You can break it up and you can dissolve it. But when you start dissolving it, ultimately what you're doing is taking CO2 out of the atmosphere. CO2 in the atmosphere dissolves in rainwater, makes a very dilute acid, and attacks, etches the rock. And when it dissolves, bits the rock, the elements recombine to form new minerals. And in the process, the CO2 that was in the atmosphere ultimately ends up in a carbonate rock. So basically the rivers are the conveyor belt taking the carbon from the land to the ocean where it's effectively removed from the atmosphere.
Both Ramo and Berner agreed that chemical weathering led to removal of CO2 from the atmosphere. But Ramo was now suggesting that global cooling over the past 50 million years was caused not by a change in seafloor spreading rates, but by a strong monsoon falling on a rising Tibet.
Generally in the textbooks that I was reading in the early 80s, people assumed that chemical weathering was a function of rainfall, land area, temperature, these factors. And according to this logic, you would think that the Amazon rainforest, for instance, would have the most chemical weathering in the world because it had all these factors. But one day I was sitting in a class and one of the professors put up some numbers on the board, and these were numbers of river discharge of dissolved material, so rock dissolved material. And it was a very high number coming out of Southeast Asia, this area. And that stimulated me to go to the original papers by the few geochemists that are out there actually measuring stuff in rivers. And when I started really digging into a lot of the recent literature, I realized that actually a lot of chemical weathering was going on in mountainous regions.
Berner's model rested on the fact that chemical weathering rates increased with temperature. But Ramo and Ruddiman took the opposite view and suggested the uplift of the Himalayas actually caused global cooling. For them, chemical weathering had increased as temperatures dropped due to the rising plateau. Were they right? Again, Tibet held the clue.
These mountains lie at the border between Nepal and Tibet. And this one, it's made entirely of granite, and this granite formed from melting of continental crust about 20 million years ago. Now, of particular interest to us is that the chemical weathering of this granite has had an important implication for the strontium isotopic composition of the world's oceans.
Strontium is important to geochemists because the ratio of two of its isotopes, strontium-87 and strontium-86, in seawater can provide a measure of the rate of chemical weathering of the continents. Here then was a test for the two models. Measure the strontium isotope ratio in ocean sediment and see if you could detect any increase or decrease on a geological timescale.
No, I just saw the buses and stuff.
The strontium record was kind of the third piece of the puzzle, I guess, that fell into place, that kind of made it all click. I knew the history of the uplift of the Himalayas. I knew there was a lot of chemical weathering going on here today, but I didn't really have I didn't really have a really good geologic record of how chemical weathering had changed through time. And when I saw a strontium isotope curve for the first time, I saw it at a meeting, and a graduate student, Don DiPaolo, showed a beautiful curve for the Cenozoic. It's just gorgeous. And I realized that this was kind of, the smoking gun, so to speak.
The lab that revealed the smoking gun? Don DiPaolo's lab at Berkeley, California, where they'd analyzed strontium isotopes from the last 100 million years of sediment.
What we found as we got further into the strontium work was that the curve got more and more interesting. The problem was we weren't exactly sure what it meant. From about 80 million years ago to 35 million years ago, almost nothing happened. And then at 35 million years ago, wham, the strontium curve starts to go up like a rocket. Now, it also turns out that at about the same time, Maureen Ramo and Rudiman had come out with their ideas about how the Himalaya and the erosion of the Himalaya were affecting the Earth's climate, and they in fact used the strontium data as evidence that erosion and weathering rates were changing, and this was support for their ideas.
However, not everyone agrees that the strontium 8786 curves are a simple measure of the rate of continental weathering. Can geochemists distinguish high weathering rates from the weathering of unusual rocks?
I think that's a very tricky question, and all I would say is that the granites formed in the Himalayas, these leucogranites, are exceptionally high in 87 strontium. The 87-86 ratio of these granites is very high indeed, much higher than almost any other granites in the world. So what we've got here is a ready source available at the surface to provide the increase in 87-86 strontium seen in the oceans. But that doesn't prove that increased chemical weathering didn't also play a role.
There's no argument that the Himalayas are the site of massive erosion. It's estimated that 6 kilometers of rock has been eroded off the mountain ranges. But erosion alone won't change the climate. For that, some of the eroded rocks must be dissolved. A two-stage model was beginning to emerge. First, Rudiman and Kutzbach suggested that an uplift of Tibet changed the movement of air masses and rainfall patterns, strengthening the Indian monsoon. The effects of that can be devastating, as people living south of the Himalayan mountain belt know only too well. Second, Ramo and others argued that the powerful monsoon falling on the Himalayas led to intense chemical weathering, stripping carbon dioxide from the air. Lower CO2 meant a cooler climate. But there's nothing to suggest that there's a limit to this process, a fundamental problem with the Ramo-Rudiman hypothesis, as expressed by Berner.
You'd run away until the whole world froze. The original paper by Ramo and co-workers in 1988 specified that if we had uplift of Himalayas, the carbon dioxide would be consumed by weathering and CO2 would go down. Well, you can't just do this simply because you have to watch out, you run out of CO2 very quickly.
The Ramo-Rudiman hypothesis took no account of the negative feedback mechanism, which keeps the Earth's climate from running out of control. And Berner's objection remains unanswered.
If you listen to Maureen, she will tell you a story that you have a hard time arguing with. And if you go to another person, for example, Bob Berner, he will tell you a story that's almost completely at odds with what Maureen will tell you, and give you good reasons why that has to be the case. And there's a real scientific problem.
Is there really a link between uplift of Tibet and climate change? Studies of microfossils from the Indian Ocean have traced the changing intensity of the monsoon. It was greatly strengthened between 7 and 9 million years ago. What was Tibet doing at that time? Fossil leaves have characteristics which are indicative of the environment in which they lived. A few isolated specimens have been found by Chinese geologists on the Tibetan plateau.
He said, this, be it a willow stem or a reed, they should be the plants on the riverbank of a temperate and relatively humid region. And that seemed to be the
Temperate.
temperate. Yeah.
Temperate.
So you wouldn't find this today in Kailash?
那肯定不可能的了。这种化石一般来说还有共生的呢，有杨树、柳树、楔树，就类似这样的化石一样的啊，都是这样的。
What did you say again?
He said that that's absolutely impossible to find this type of plants in the modern innovation or the attitude of Kailash. And there are
The difficulty is that a wide range of fossil leaves is required to define the temperature zone of their habitat. And then to relate that temperature to altitude is problematic too. Another way of looking at the elevation history is to look for geological faults. Here, for example, the foreground terrain has slipped downwards, leaving what was once a cliff face now eroded into minor peaks.
There are hundreds of normal faults like this in Tibet today, and this fault is active. There's likely to be an earthquake on this fault any time. So if we can date when these faults become active, that will tell us when this change took place, when the change from building a plateau to destroying a plateau took place.
These faults relate to the time when the Tibetan plateau had reached its critical altitude and then began to collapse. The time at which the fault was active turns out to be sometime between 5 and 11 million years ago. This is the same time that the monsoon strengthened. Scientists like Peter Molnar are now trying to establish a causal link between the two events.
The forefront of science is a very fuzzy area, and one needs a balance of all kinds of approaches. There have to be ideas drifting around, they have to be formulated and worked up well, and usually when they are, there still aren't enough facts. And then there are the rest of us who go out and try to find facts that test them.
The next fault to be dated came in at 14 million years, which is older than the change in the monsoon. Contradictions remain. Did the scientists visiting Tibet reach any different conclusions about the Ramo-Ruddiman hypothesis?
I think it's one of the most interesting ideas to have developed. I should say that geologists are inclined to favour the idea because it does involve physical processes that they're interested in. But I really haven't seen anything in the last 3 weeks which would persuade me that this is a scientific truth. But it remains an interesting concept.
The jury is still out on whether the mountains and plateau cause climate change or are just a part of the feedback mechanism that stops the Earth's climate overheating. But there's no doubt that the uplift of the highest and the largest plateau on Earth coincides with a period of extraordinary global cooling.